Hello everyone. Today we are going to discuss one of the A to D converter, that is analog to digital converter. So this A to D converters are nothing but it is going to convert analog voltage to the digital output. As in the case of digital to analog converters are specified as 8, 10, 12 or 16 bit. There are many types of A to D converters are available. Those are single ramp integrating, dual ramp integrating, single counter, tracking and successive approximation. These are the various types of analog to digital converters. So in this section we are going to discuss about successive approximation type, an analog to digital converter, which uses a comparator, successive approximation register, output latches and D to A converter. Okay, so this figure which shows the successive approximation type of A to D converter. So the heart of this A to D converter is nothing but this 8-bit SAR, that is successive approximation register, whose output is applied. You can see here this is an 8-bit, so there will be 8 different outputs from this register, Q0 to Q7. Q7 is a MSB bit, Q0 is a LSB bit. So like that you have got 8 different bits, Q0 to Q7. So the output of this SAR is fed to the 8-bit DAC, that is digital to analog converter. Okay, so these are nothing but now binary inputs. Okay, it is specified here whatever the output of this SAR is there, that is nothing but binary input. So that will be the input for your digital to analog converter. So what is the operation of digital to analog converter? Which is going to convert the digital inputs, that is binary inputs, to analog one. Okay, so you will be getting only one output from 8-bit DAC, that is mentioned as here analog voltage out VA, that is applied as the input for the comparator, that is inverting input for the comparator, and to this comparator we are providing one more input, that is nothing but your actual analog input Vin. Okay, so how this analog input is converted to digital, that we are going to see here. So the actual analog input is fed to the non-inverting terminal of the comparator. So comparator, it compares these two, okay, and which is going to provide the output. That output is fed as the input to your 8-bit SAR. So according to this input, the various binary inputs of SAR, we are going to get. It is going to set or clear. Q7 to Q0 to Q7 is going to set or reset depending upon the serial data given by the comparator. Okay, so apart from this we can see here clock signal. So according to the clock it is going to generate the output, and one more output is serial data out D0, and S is a start, that is start of conversion starts by enabling this button, and CC is nothing but conversion complete, means after the conversion, that is after your Q0 bit is tried, then the conversion is going to complete. So this is going to enable that particular end of conversion. And then apart from this, the outputs of the SAR, it is nothing but the digital output, which we are going to feed to a 8-bit latch. So 8-bit latch, just it is going to hold the digital output, and then we will be taking that output wherever we require. Okay, so this is the operation of your SAR. Now let us see how the operation it is going to do. Okay, so first, as I said, start of conversion. So at the start of conversion cycle, the SAR is set by holding the start signal high. So by setting this start signal high, the conversion is going to start. So on the first clock pulse, either low to high or high to low transition. Here they have mentioned as low to high transition. Whenever the clock reaches the low to high transition, your conversion is going to start. Okay. So initially S will be high, then it is going to check the clock pulse whether the clock pulse has reached low to high transition. According to that, it will take the it will provide the output. So here the D on the first clock pulse, low to high transition, the most significant output bit, that is Q7 of the SAR, is set. For the first clock pulse, this will be set. Okay, this will be set means logical value is 1. Reset means logical value is 0. So this will be set for the first clock pulse, and the D to A converter then generates the analog equivalent to the Q7 bit. That is, whenever Q7 is high, all the other bits will be 0, means it is 1 0 0 0 0 0 0 0. So the DAC that will be given as the input for your digital to analog converter. So this will convert this binary inputs to a analog one. So you'll be getting the analog equivalent of this Q7 bit as high. That will be compared with your analog input Vin. So comparator, how the comparator generates the output, that is, if the comparator output is low, indicates that your VA, which will be greater than Vin. If VA is greater than Vin, comparator output is low, means it is 0. Okay. Suppose if VA is less than Vin, means Vin is greater than VA, then you will be getting the comparator output as 1. Now suppose the comparator output is low, what is going to happen? Low means if the comparator output is low, then it will clear the MSB bit. Initially it was set, Q7 was set. Comparator output we got this as 0. 0. If this is 0, it is going to clear the Q7 bit. Suppose if comparator output is 1, that indicates that it is a true condition. So this will be under set condition only. So it will keep high only. Then for the next clock pulse, it is going to check the Q6. It is going to set the Q6 bits. Anything might be the output of Q7, either 0 or 1. It is going to set Q6, and thereafter it is going to continue depending upon the comparator output. If comparator output is 0, then the bit will be cleared. If this is 1, the bit value will be retained as it is. That is, 1 will be retained as it is, and then that will be converted to an analog that will be given as an input for the comparator. Again, the same process it is going to repeat until the least significant bit is reached. So until Q0 is tried, this process is going to happen like this. So once Q0 is tried, then what happens? Your conversion complete signal, it will go high. Means we have reached the end of the conversion. That indicates that if this signal goes high, indicates that it is the end of conversion, and that equivalent digital output will be stored in the latch, and thereby we can make use of those digital data output. So this is how your successive approximation A to D converter it is going to operate. Okay. So next is the explanation I had given here, that is, heart of the circuit is an 8-bit successive approximation register whose output is applied to an 8-bit DAC, and then analog output VA is generated by D to A converter that will be then compared with your analog input signal Vin by the comparator. The output of the comparator is a serial data input to the SAR, that is successive approximation register 8-bit. Then the SAR will adjust its digital output until it is equivalent to analog input Vin. So then the 8-bit latch at the end of conversion holds on to the resultant digital output. Then the circuit works as follows, that is, initially the start of conversion, it will go high. Then we will check the clock pulse, low to high transition first clock pulse, where MSB Q7 of the SAR will be set. Then the D to A converter generates the analog equivalent to Q7 bit, which is compared with the analog input Vin. If the comparator output is low, then the SAR will clear the MSB Q7. On the other hand, if the comparator output is high, the D to A output, which will be lesser than Vin, then the SAR will keep MSB as Q7 as set. In any case, on the next clock pulse, what happens? Your SAR will then set the next MSB Q6 depending on the comparator output. The SAR will then adjust either reset or reset the Q6 bit. This process is continued until SAR tries all the bits. As soon as the least significant bit, that is Q0, is tried, SAR forces the conversion complete, that is CC signal high, to indicate that parallel output lines contains the valid data. So CC enables latch and digital output appears at the output of the latch. So this is one example I have taken. Here I have not taken 8-bit successive approximation ADC. I have taken only the 4-bit. So here I have considered only 4-bit. I have taken to compare the 4 bits. To compare the 4 bits, I require 4 clock pulses. Okay. So the first waveform, which is nothing but SOC, start of conversion. Then the end of conversion, EOC is given. Okay. So first we'll check for this will be the input for your 8-bit SAR. So if SOC, that is start of conversion, start signal is high, then it will check the clock signal. So the first clock signal, in this we are going to compare the MSB bit. Okay, that is Q7 in our case, previous case. Here it is mentioned as MSB as D1 and LSB as D4. There it was MSB was Q7, LSB was Q0. So in that manner, if we take means this will be Q3 and this will be Q0. Okay. So let us start. So this first clock pulse to compare the most significant bit D1. Second one to compare the next bit D2. And third one to compare D3. And fourth one to compare D4. Okay. So now what happens? Initially when the start signal is high, compare the first clock pulse is achieved. That is during the first clock pulse, low to high transition, your MSB bit, that is D1, will go high. So it is 1 0 0 0. Means the analog equivalent of this is 8, right? So 8. So now this is nothing but analog equivalent, that is output of the DAC is nothing but 8 now. So VD, which will be compared with your VA. So if VD is greater than VA, sorry, this is VD, that is compared with your VA. So now VD is greater than VA. Digital output is greater than VA means what is going to happen? Output of the comparator will be low. If it is low, it is going to clear the most significant bit. So VD is greater than VA means the most significant bit it is going to clear. If it is no, then it will be retained as it is. Means this one, it is retained as it is here. Okay, you understood this point? If VD is greater than VA, that is digital output, analog output of the comparator, analog output of the DAC is greater than the analog input, actual analog input VA, then it is going to clear, because output of the comparator is low, it is going to clear the MSB bit. Otherwise, it is going to retain the same state. Okay, so 1 is retained as it is. So here it is 0 1 0 0. Next is here is 1 1 0 0. So what is analog equivalent of 0 1 0 0? 0 1 0 0 is nothing but 4. Okay, now again this will be given as the input for your comparator. Comparator will check with that with your analog input. So if VD is greater than VA, what happens? This bit it is going to clear. So it is 0 0. Whereas here 0 1 is retained as it is. Okay, next here again the analog equivalent is different. Here it was 4, here it is 2. So whatever might be your previous outputs, either 0 or 1, for the next conversion, it is going to set the bit, that is 1 1. So 0 0 1 1. Again it is compared with your VA, and then if it is yes, it is going to clear this bit, third bit, and then here it is going to retain as, sorry, here it is going to retain as it is. Next again, the next bit will be high. If that will be compared with your VA analog input, and then what happens here? If it is yes, then all the bits will be cleared. If it is no, next 0 0 0 last bit will be set. Okay, and here no path we have not considered. Next we shall see this. No means 0 0 1 1. Now we are checking the last bit. If it is yes, what happens? That bit will be cleared. If it is no, then it will be set. Same thing for the other types also we have considered. So you can go through all the things. So it is very easy. It is similar to this. Okay, so next when I come to the advantages of successive approximation register, it will be high in speed. Okay, so successive approximation register, it is high in speed, and then excellent resolution you may get from this successive approximation register. So while writing in the exam, what and all you need to write down is this picture is very important. This carries more marks. So if it is asked for 8 marks, I think 3 to 4 marks will be given for this figure, and then this explanation regarding the figure, and then the circuit operation, how it is going to operate. This explanation you need to give for 8-bit only, because in the figure 8-bit SAR, 8-bit is 8-bit ADC it has been explained. And then one example, any doesn't matter whatever the bits you have taken, you may take for a 4-bit, 3-bit, anything you can take. So this I had given for 4-bit, and any one example you can take here and you can provide it. Suppose if I take here analog input as 4. Okay, and that is VA is 4, that will be compared with 8. 8 is greater than VA, that is 8. 8 is greater than 4, so it will follow this path. Again, now here 4 will be compared with 4. It is not greater, so what is going to happen? It will follow which path it will follow? It will follow no path, because it is not greater, lesser than or equal, it will be going for your this path. So 0 1, this bit is written as it is. Next you are going to check whether your VD, that is VD means this one, 6 is greater than 4. 6 is greater than 4, yes, this path. So this is 0 1 0 1, so it will be compared with your 5. Again it is greater, yes, so this is your actual answer, 0 1 0 0. So this is the path it is going to follow. This is how the successive approximation type ADC it is going to work. And then you have to mention about the advantages. Two advantages: high in speed and excellent resolution. Okay, I hope you understood. If you have any queries, you can mail me, and then yeah, see you in the next session. Thank you.